Welcome to Prof.Ahilaa Maths, Plus 2 Mathematics, Tamil Nadu State Board Syllabus, Chapter 1, Application of Matrices and Determinants, Video 1.5, Theorem 1.4, 1.5 and 1.6. 1.2.3 Properties of Inverses of Matrices. Theorem 1.4, if A is non-singular, then first part, determinant A inverse equal to 1 by determinant A. Second part, A transpose the whole inverse equal to A inverse the whole transpose. Third one, lambda A the whole inverse equal to 1 by lambda into A inverse, where lambda is a non-zero scalar. Let us see how to prove this. Theorem 1.4 proof of first part. See the steps. In the question, it was given A is non-singular, so that we know determinant A not equal to 0. Therefore, we know A inverse exists. These are all conditions for existence of A inverse. And by the definition of A inverse, we know A into A inverse equal to A inverse into A equal to identity matrix of order n. Now, we need to prove determinant A inverse equal to 1 by determinant A. Remember the first equation. So, take determinant of the first equation throughout. So, we will be getting determinant A into A inverse equal to determinant A inverse into A equal to determinant In. So, using the product rule of determinant, we split the determinant to each factor, so that determinant A into determinant A inverse equal to determinant A inverse into determinant A equal to determinant In. We know determinant In equal to 1. Now we are getting determinant A inverse into determinant A equal to 1. So that determinant A inverse equal to, we can cross multiply by the determinant A in the right side. So 1 by determinant A. Clear? Now let us see the proof of the second part. We need to prove A transpose the whole inverse equal to A inverse the whole transpose. Now remember the first equation again, that is the definition of A inverse. Taking transpose of equation 1 throughout, we will be getting A into A inverse the whole transpose equal to A inverse into A the whole transpose equal to In the transpose. We know In transpose equal to In itself, okay, and see, already you have studied that reversal law of transpose. That is AB the whole transpose means we have to reverse the transposes, okay. So B transpose into A transpose. Similarly here A inverse the whole transpose equal to, first revert it, A inverse the whole transpose into A transpose. Similarly the next case, A transpose into A inverse the whole transpose equal to, already we know In transpose equal to In. So consider any one part, so that by definition of inverse we know whichever matrix, when it is multiplied with the particular A matrix, we are getting In means that matrix will be the inverse of the matrix A. So here the highlighted yellow colored thing is the inverse of A transpose. So when we write in notations, we will be writing A transpose the whole inverse equal to A inverse the whole transpose. Got it? Good. Let us see the proof of the third part of theorem 1.4. We need to prove lambda A the whole inverse equal to 1 by lambda into A inverse. In the question it is given lambda is a non-zero scalar. So we can multiply and divide wherever needed by this lambda. Here we are multiplying and dividing by this lambda in equation 1. Only thing you have to remember is you need to associate this multiplication of lambda with A and division of lambda with the A inverse. Keep it in mind. So that we are getting lambda A into 1 by lambda A power minus 1 equal to 1 by lambda A power minus 1 into lambda A equal to In. So you know that division and multiplying by the particular number will give you 1 only. Okay, instead of 1 we are replacing lambda by lambda. So now we are getting lambda A the whole inverse equal to 1 by lambda into A inverse. That is, when this highlighted yellow part, when we multiply with lambda A, we are getting In. By definition of inverse, this highlighted part will be the inverse of lambda A. So we are saying lambda A inverse equal to 1 by lambda into A inverse. Hope you have got it. Theorem 1.5, left cancellation law. Let capital A, B and C be square matrices of order n. If capital A is non-singular and AB equal to AC, then B equal to C. Let's see the proof. Given A is non-singular, therefore you know A inverse exists. This is the condition for existence of inverse. By the definition of inverse, you can write A into A inverse equal to A inverse into A equal to In. Also in the question it is given AB equal to AC. So take this definition of inverse as equation 1 and AB equal to AC as equation 2. Now we need to prove B equal to C. Just pre-multiply equation 2 by A inverse. Consider equation 2 and pre-multiply by A inverse. See the highlighted part. So A inverse into AB equal to A inverse into AC. Now we know matrix multiplication is associative. So associate A inverse and A together. So A inverse into A into B equal to A inverse into A into C. So A inverse into A will give you In. So In into B equal to In into C. You know In into B is B and In into C is C itself. So we are getting B equal to C. Theorem 1.6, right cancellation law. Let capital A, B and C be square matrices of order n. If capital A is non-singular and BA equal to CA, then B equal to C. Similar to the previous proof, we are considering A as non-singular. It is the given condition A. Therefore, A inverse exists. That is the condition for the existence of inverse. By definition of inverse, A into A inverse equal to A inverse into A equal to In. Keep this as equation 1. Now, also it is given BA equal to CA. So, keep this as equation 2. Now, we need to prove B equal to C. Here we just post multiply equation 2 by A inverse. In the similar steps, we post multiply. That's the difference between the previous theorem and this one. So, BA into A inverse equal to CA into A inverse. That is, matrix multiplication is associative. So, use the property B into A into A inverse equal to C into A inverse. Now, again B into In equal to C into In will give you B equal to C. Fine. Let us discuss a note given in your book. If A is singular and AB equal to AC or BA equal to CA does not mean B equal to C. So in the previous cancellation laws, the main condition is A is non-singular, and if it holds any of these two conditions, AB equal to AC or BA equal to CA, then only B equal to C. Suppose A is singular. Let us discuss by an example given in your book. So consider capital A equal to 1, 1, 2, 2, B equal to 1 minus 1, 1, 0, 1 and C equal to 0 minus 1, 1, 1. Clearly determinant A equal to 2 minus 2 which is 0 and so A is singular. Now we check the product of the matrices AB. We are getting 1, 0, 2, 0 and AC also 1, 0, 2, 0. So now we are getting AB equal to AC. But you can observe that B and C are not equal. So the main condition A should be non-singular if this cancellation laws to, to hold. Okay. So when I check for the other case BA equal to CA, here BA and CA we are getting different matrices. So BA not equal to CA, in this case we don't want to consider the thing. Okay. So only for if A is singular and any of these two conditions holds, then it does not mean B equal to C. Clear? Now remember, my dear children, only if A is non-singular, the left cancellation law and right cancellation law holds. That is, AB equal to AC implies B equal to C, or if BA equal to CA implies B equal to C. Video 1.6 contents are Assignment 1.2, Exercise 1.1, 3, 4, 5 problems, and the problems are these three. Try your solving first and we'll discuss in the next video. Stay tuned. Success is ours. Thank you, my dear children.